Hello, everybody. Thank you for the invitation. We have seen a lot of presentations for the thermal bridges, and yeah, we've seen some also study cases or references, like the last one, for example, with the hollow core slabs. I will go a little bit further, also explaining a little bit of the thermal break products that we offer, and especially this other important topic, because I think it's a really important and delicate topic, which is the thermal expansion that suffer those elements. So yeah, okay, after what our colleagues explained before, we know the basics, right? What is a thermal bridge and the need of that, and how this thermal break works. So just as an introduction about, okay, balconies. Yeah, well, let's say balconies are quite dangerous structures, let's say, because for the obvious reasons we have sometimes high loads, especially on cantilever balconies. So yeah, those are really susceptible areas because, for example, in the design, those are actually isostatic structures, so you cannot count in the redistribution of forces or loads if one of the support or the connection elements fails. So, for example, in this case, okay, this is like a collapse example of a balcony. Here was supposed to be a balcony, and you see some mold formation here. What happened is, well, you have this element exposed, right, the whole life for the next 50 years to wind, to sun, to snow. So what happened, it's a good example. This is not a thermal break connection. Let's say it's just like a standard connection balcony, but it helps to make my point clear. You get to see it, well, the black marks, obviously some, how do you call this? Something happening like here, right? In the balcony, this creates some moisture and some corrosion, and at the end, what happens is the balcony tends to collapse. If you are here in the construction industry, well, it may seem clear for some of us, but the thing with balconies is no one is checking the balconies in the next 10 or 20 years. So this is very important because when you design your project, your balcony also needs to stand 50 years, the lifetime of the building. So we have to keep in mind that this is a sensitive part, and it's important because all those weather conditions that our balcony is exposed to. And this is, let's say, even assuming that the balcony is properly used. So here we have another example. This is an article in Germany, but just say that, yeah, some people thought that it would be a good idea to put a pool in the balcony because at the end, why not, right? To put a pool over there. But what happened, okay, the reason is, imagine the weight of, let's say, 40 to 50 centimeters of water. The balcony was not supposed to work with that load, and yeah, so people may change the conditions too, and something you cannot control, and yeah, it's important to pay attention to that too. Also, okay, this is another example of a collapse. Who is the responsible? Okay, this is, well, not a balcony actually. You get to see these yellow strips or bands. What happened here is that, well, they thought that will be a good idea to close this space, so you will gain an extra space from the inside, you may say. But the problem is the same. You get to see, you close the space, create some condensation, some moisture that at the end will lead to corrosion. And this is what happened here. Those steel elements fail. And yeah, this is also a good opportunity to point out the need or the importance of stainless steel, right? Because you will get some condensation, of course, in those areas. If your insulation layers fail or something, you will get also some water, and so that's a really important to pay attention to. And in the right side here of the screen, you get to see this is a screenshot of an American attorney. Well, but this can also happen here in Europe too. What happened is, because with those let's say collapses or problems that may occur with your balcony, the question at the end, who is going to pay for that, right? There's people that it's lends their service to ask for money or compensation, and this is also really important because at the end of the day, well, the guarantee of the building is one thing, but the responsibility for the engineers and the designers and everything will stand for longer years in some cases. So this is important too. Yeah, we need to pay attention to the design on balconies. I'm going to explain a little bit of that a design process for a thermal break, because it's not just the isocore, not only our product. This is a design process that should be followed for every thermal break system. To do a design properly designed. So we will just aquí summarize the steps, analyze the structure, pick up the right element, calculate the forces, right? The forces we need to withstand with our system. We pick up the right reference, the right model that withstand the loads that we have. And also, well, pretty important to communicate that information to the building sites. And the first step is to check that we don't have any bracing connections for our thermal breaks, because of the difference of rigidity. We cannot have rigid connections for our thermal break system. So, for example, this one we see here, this green one, it's okay, because this is a cantilever, it's not a bracing connection. It's possible to have a thermal break there. The other ones you get to see, for example, this marked in red, those for sure are bracing connections. So the thing is, we cannot put let's say a thermal break over there because of that same reason. The rigidity of the connection of the system is not compatible. And okay. And also, well, we have these other yellow ones. Those require further analysis. It's not so obvious if the connection depends or not in a bracing connection too. So we need to follow this let's say sentences here to check that we can apply this element. The second step is to pick up the right type. As we saw before, well, we have a lot of products or elements that are used in different situations. Here we have the cantilever, the most common one, right? Or if I have a supported balcony, we can use this other product that just deals with the shear force, or a slab edge. If I have let's say a wall here in my facade. Some other examples. Here we have, for example, for parapets, also for concrete beams. This is coming, well, actually in just one side, but this is pretty useful if you have a concrete to concrete connection on bigger beams. Also to show that we can do this type of connection in corners, so you get to see all the rebar going in both directions. Well, we do that in our design already came with with this taken into consideration. And this other last one here in the right lower corner, it's for, let's say, connections where we cannot extend our bars. For example, if I have to do a connection from a balcony to a wall, this will be the ideal product because we can anchor these forces and everything to the wall, and we don't need to continue with the rebar. So yeah, once we find out what is our situation and we define it, we proceed with the calculation of the forces, right? The forces that act on your balcony, let's say, or it can be a parapet or any other element. So we have the gravitational forces, like the more obvious ones, or the live loads, you can say, right? But we also need to consider, for example, in steel balconies or parapets, we have green forces. In some other cases, if some of you have projects not in the Baltics but abroad, you may have some seismic conditions. So yeah, according to the Eurocode 8, we also apply the design for those earthquake forces. Here, well, it explains how to calculate it. And again, if you have any project that you need help with, yeah, you can get in contact with our partner here or with us directly, and we can help you with that. And the last one, it's also a really important one, is the thermal expansion. Well, for this one, I will talk a little bit more later. And yes, well, this is an example. I want to show an example of how is designed the, let's say, the connection. But actually, this one is a bad example. I wanted to point out the importance of doing right the design. For example, here the client or the designer well has its balcony here, and you get to see the connection in this light blue line. We have also a column here, so that's the scenario. We don't have any walls. So yeah, the designer says, okay, around 1.5 meters, we have this, for example, 70 kilonewtons per meter shear force. And after that, we have, let's say, 15. But here's the importance of doing right the design. Because actually here, the designer, what he did was he modeled the whole slab, all the inner slab, with the balcony as a piece, as a monolithic, both together. And this is where the problem is, because what he did was, okay, he modeled everything and just passed the line here where my connection is supposed to be, with my thermal break it's supposed to be. And yeah, right click and show me the diagrams of the forces. And the problem with that is, okay, you get to see the results here, for example, for moment. This is the diagram for moment. You get to see values from 0 to 10, let's say in this area, in this side. And yeah, I will point out the risk of proceeding this way, because if you consider those are the forces acting on your thermal break system, let's say if we compare it with the good design, you will notice the difference. So here's how you are supposed to do it. We model our balcony apart, also well, using the FAM software to model it also. But we need to consider here the proper stiffness of the connection, right? This is, as I say, this is not a bracing connection, it's more like a spring connection. We take these considerations, and after that we can run our model and obtain our forces diagrams. And with those forces, we apply it to the connection, to the inner slab. We apply those results over there, because those are the forces that will be transmitted to our slab. And this is what you get. I just want to drag your attention to the previous slide, where the momentum was way lower. You get to see from 0 to 10 in this area, for example. And if you do the design properly, you get to see here right? When we do the FAM analysis and apply the forces, you get to see the difference already in the colors. And here you can see it. We have values from 0 to 30 positive momentum just in this area, which is the same one. And yeah, by the way, this is the same for the shear. And also really important because you get to see we had a column here, if you remember. And this is important because now, if we do the design how it's supposed to be, we only have 3 faces for that column, for the punctual the punctual or shear that can occur around that column. And this is really important because you get to see if the analysis was made this way, I have a bigger area to withstand those punctual or shear forces around my column. But in the reality, I don't have that. I don't have that big area on this side. So just only 3 sides instead of 4. So yeah, the problem with that is you may end up under designing your connection. So it's we need to take that into consideration. And after we do the design properly, we can now, let's say, select your right product to that. So again, we do this design for you. For example, this is just to show the procedure and how to do it manually, because you get to see here, this is a table, a typical table you can find in the technical manual. And for example, we have here an example to see it, how it works. We have a height of slab of 2000 millimeters. So we go to our table, find here our thickness in our slab. And let's say we need to withstand 35 kilonewtons negative for our bending moment. So we go this way, this one is not enough. We go to the next one and that's it. This is the product range that we can use to withstand this moment. And for the shear force is the same. We have 32 kilonewtons positive. So we go to the lower part of the table where we have the shear resistance, and we can go with this one because we can withstand it. It says 60. It's almost double as our need. So yeah, we'll be fine with the CM20 for this case. And yes, now that you have your thermal break, this is an example, but it's also really important communicating this information to site, right? Because we do all the calculations, but getting the information to the people that need it is also important to deliver the right information. So let's make people understand. That's the thing. And this is a pretty elaborate example, but we can provide these draws, and what is shown here is just the size of the isocorp, the space that it needs, and the product. Just to have all ready for installation. And this is more about the way to do a design. Now I'm going to explain a little bit of the isocorp, how it works. Of course, this is not just insulation as we saw in the previous presentation. This is also structural. Here is an example or similar to the samples we have in the entrance. But here what we do is we show transparent the insulation. This is the element for a cantilever concrete to concrete connection. We have the steel, of course, the upper steel to support the bending moments. Here is the steel for the shear forces. And you may see in this central area that it's a little bit more shiny or bright color. It's because of that. That's more shiny. This is a stainless steel. So this is important. Why? As we mentioned before, because of the corrosion, we can put this on site. There's no problem to leave it outside, to leave it under the weather conditions. It may get rain and everything. And that's an advantage also if we compare it with, let's say, a mineral wool. because it will get some damage. So for this one, it's not a big problem. So at the end, when I'm going to install the product, I will get some, let's say, some humidity inside the steel. And the problem with that is, yeah, it will lead to corrosion. Also, another case could be, let's say we have, with the time, a crack that grows here in this area where the concrete is. We may have some leak or water or whatever. So yeah, it's important to have this part protected. Also, the third reason is this is passing by. You get to see it. It's passing by, crossing the element, and this steel is not covered by concrete. This is the main reason too, because it will be exposed its whole life. So it's important to keep it integrated. And yeah, okay, this is more about the reinforcement. Yeah, with this, well, we about all rust problems. And you get to see here in the lower part, the compression models. We use these compression models that we developed. It's what my colleague mentioned before. Here is where we withstand all these compression forces. And you get to see this in blue is a plastic cover actually. And inside we have this high density concrete that support the compression for the elements. And on the upper and lower part, what we have here are just fire resistant plates, because this is what gives us resistance up to 2 hours in case of a fire. And yeah, this is pretty much it. The parts of the isocore. Oh, okay, I almost forgot this other black strip. You get to see it here. Is also intumescent strip. This material expands in case of a fire, so you get to preserve the core longer, because in fire this crack may expand, and so yeah, we use this element to seal the gap for a little bit longer. Yeah, here's the similar product we also mentioned before, that my colleague mentioned before. This is also the isocore, but this is the CXT, where we replace the upper bars with fiberglass, which doesn't corrode. The thermal conductivity is way better, and yeah, well, has lower values actually than even than the stainless steel. So yeah, this is like the improved version. Yes, okay. This is the mechanical principle. Again, this is not something you got to do by yourself. We provide the tables with the designs and everything, but I think it's important to mention how does everything works inside the isocore. For example, you may have a balcony here on the right, and on the left we have a wall. For our example, we have our forces that they are acting on our balcony, and yeah, let's say here using this truss system, we have our tension stud, also shear stud and compression studs. And yeah, okay, I mean, we can write the equations and everything will be equal to 0, because yeah, of course the system is balanced and nothing is moving. So yes, here's all the elements for the principle. And when you write the equations, you develop them, and yeah, you write them into the terms of the acting force. So you get to have the forces that need to withstand each of your studs. And if you reverse those equations, you get the maximal forces that your product needs to withstand, depending on the force of each stud. For example, if we take this one, the tension stud, let's say we have 10 bars of diameter 8. So yeah, my resistance of this bar 10 times, so it will be the resistance of my stud here, of my tensional stud. And with that, we can calculate the maximal forces, and yeah, you get to see the resistance of your isocore with those forces. Again, well, this is just the principle, the physical way to do it, but it's not something you got to do. Talking a little bit about our research and development department. Okay, our R&D has two sides, or two parts, you get to say. The quality control, where we test our products. You get to see here this tension test for the steel bars, or this compression models are being tested here with this hydraulic press. So yeah, we have several guys every day in the factory doing quality control just for those tests to see that the materials are behaving the right way. And yeah, the second part of our R&D is the lab where we develop our products. Actually, you get to see here a picture. It's not so easy to see, but because for the test we need these big beams to fix this slab. You get to see this is our inner slab for the test. In the isocorp, it's around something like here. Here we apply the force as a cantilever. You get to see the rest of the balcony here. And yeah, it's an example of the types of testings we do in our R&D. Yeah, I'm going to show you an example of a test we do on our R&D, and for that I will use the topic of thermal expansion. So let's start with a short explanation of what the thermal expansion is. You get to see it here in your balconies, for example. Well, the balcony, it's for obvious reason outside, so it will become colder in the winter times and warmer in the summer times. And because of that, it will lead to contraction and expansions that will create small movements. It's, again, really small. We may be talking about 2 millimeters, but yeah, it has real consequences on your system, and this is why we need to take those into consideration. So here is an example. Let's say we have a balcony of 11 meters per 2 meters wide, and yeah, we assume a difference temperature of 35 K because, well, it's expressed in the norm. We can see that later. And what happened here in the balcony is the element in the middle. Oh, sorry. In the middle, it won't feel that phenomenon of that thermal expansion. But the elements on the right, yeah, you get to see that we have differential of, let's say in this case, 2 millimeters this way and 2 millimeters this way. This expansion that is happening because of the temperature differential. For corner balconies, well, we got the same behavior, but what happened is here's the fixed point and the movement, it's in these directions. Now, yeah, we can have a look of how our thermal system behaves. So of course, in the middle, you get to see it here is no movement, is 0.0. But in the edge, you get to see the displacement that was created. Of course, this is exaggerated just to show the idea, but we need to accommodate to these displacements, and you cannot stop it. You need to deal with these forces, and this is the way that will happen anyway. So that's what is important to learn how to deal with that. If we have a closer look here, you get to see this. We have a tension and compression in our element. See, fixed both ways. So those areas, if we're talking about the bars, the physics behind that is the same. We're speaking about bars, but it could be the same for beams as an example. It's just a question of scale. And yeah, okay. If we take an even closer look, you get to see this rotation that we have in these fibers. So what happened here is, well, these fibers become smaller, but the other ones are here, those elongates. So the thing is, the bigger is the distance from the neutral axis, the bigger will be this deformation and this elongation. So what does it mean? It means more stress in our fibers just because of this movement that is, again, like microscopical, but if you do it in the test, you get to see it. It's also really important. We have the formula for stress here. You see our lambda, and yeah, for our forces. For this example, well, we have the displacement of this situation. L is the thickness of our, we said, our thermal brake system, that it's fixed in both edges. And yeah, the stress bars are, well, it happens because of all of this formula. Each side you get to see, okay, we have the forces in each side because we have an equilibrium. But the important thing here is, if we take a closer look to the values, that depends. It depends a lot on the Young model, and why the area is related to the size of the system and the thickness of the thermal brake system. Because when you develop your thermal brake, you want to be the stress as lower as possible. So, because this stress at the end is the stress that the bars feel, but also is transmitted to the concrete, and this is where it's not good, because concrete is not so good to deal with that stress in some situations. So we need to have this value as lower as possible. We in Schöck use a stainless steel that has a even lower E value. So this is, well, just part of an example of how we take those considerations to develop when we develop our system. So yeah, here we have an example. This theoretical values. I got here listed, for example, bars of 8 and 12 millimeters, because those are the ones we can also use in our isocorp. Also, we have plates here 10 by 50, 10 by 100 as an example, and a beam. So if we compare, let's say, the forces we get for a bar of 8 millimeters, you get to see it. It's not so much. I mean, the concrete can withstand this force. It's not a problem. But let's say if we take the 12 millimeters, well, you see the force is going up. And yeah, this is because it's the force that is acting on our surrounding concrete is what is important to take into consideration. Because if you get to see, the smaller the element, the smaller the force. So this is why it's important to have lower or smaller section elements in our thermal system. Again, those are theoretical values, right? Because you get to see it here. Let's say for this plate of 10 by 50, you get a force of 300 kilonewtons in our concrete. This won't happen, most probably, because at some point the concrete will crack and that tension will be released. So you won't reach this value. It's just theoretical. So that's the thing. But it's not, of course, it's not good at all, because the cracks will release that force, you get to say, but this cracks needs to be small enough to still protect our concrete, or otherwise will be a big problem. And yeah. Now we have a look of this other example, this other text. This is a perfect fixation I was talking about, right? You get to see in the upper and the lower part, and you get to see here the perfect S shape, but it's not perfect at all. In the real conditions, it's less stiff. So this will create here some point a lot of energy that will transmit it to my concrete and will create a lot of cracks. And yeah, so here's a bigger spacement, but it's just you get to see also here the shape. It's already curved, or has this shape already reached the plastification there. So remember, this has to withstand or to remain for the next 50 years, even with cracks, even with everything. So this is why it's important to have all this into consideration in the development of the system. And yeah, if we continue with the elements here, another problem we may have is the buckling in our compression elements. So you get to see here this tray element. It will withstand more force than this one, of course, because we have the axis move already where the force is applied. So here is better to withstand the force because it's not deformed also. And yeah, at the right, you get to see the different development we had for our compression modules over the past of the years. So we're now working with this one. This is as I said before, a plastic cover, and you get to see just the concrete pour over there. So here is a closer look. If we have a section of our compression model, this is how it looks. And yeah, you get to see the round shape here too. This is pretty important. It's part of this almost 40 years of research and development because it's made for this same reason. So we can have this movement that the compression model will move and not bend. This is what happened here. So we have the round shape in this way and also in the upper way because of the weight of my balcony or my element will also influence and make this as a reaction in an angle. So this is why we have this curve here. And yes. The last effect that can happen or actually happens in our thermal brake system is the fatigue. Yeah, for example, if you take, let's say, a spoon and you bend it several times, at the end you will break it because you already, let's say, weakened that material. And this is what happened with fatigue. It's the same effect, and it also happens in our system. So it happens even if you don't reach the plastification, because even if you reach 20 or 30% of your capacity, it will have a real impact after 1,000 cycles. And this is what we do in our tests too. We test that. This is a chart for stainless steel. It's not ours because ours can reach up to 800 MPa. But yeah, for example, you get to see this is a 350 MPa stainless steel, but you see it after 1,000 cycles. You see how it drops, how the capacity drops, and yeah, it's important. It's almost a 30% range drop. So definitely something we must take into consideration. And yeah, in our balconies or in our elements, what is that fatigue? So this is our daily variation, day-night cycles, weather variations, and yeah, season variations. All of those create smaller or bigger cycles that will happen all the time for the next 50 years. So yeah, the isocorp, as we mentioned, is a certificate with the ATA. If you want the certification for the ATA, well, we need to follow the requirements of this document called AAD. And for the system, here it gives you how many cycles you need to fulfill in a different range of temperature. So yeah, we do over 20,000 cycles for that. So this is something that you need to consider when you use this kind of system, this thermal brake system, because these approvals, when you design this, or for us that we design these products, it needs to be done. Here we have more pictures of our, let's say, of horizontal press, and yeah, in the other side we see a test already done. You get to see the balcony already fail. So this is what we do. We have the inner slab, let's say, for example, and here is the isocorp. already failed because we applied here the, let's say, the cycles, and at the end we applied the force. And yeah, despite that, all that research we do, it's important to point out that if you take an isocorp brand new from the production line and you compare it with one that has been through this whole process, you get to see there's a really important difference in the capacity and the resistance. So this is why it's a really important topic. It has a real impact. So it's important to make sure that you use products that has this kind of certifications. Okay, now again, when using, this is also of course for the isocorp. This is the table we got for the ATA approval. What this table says is depending on the thickness of our insulation. We have the two sizes of our isocorp, 80 millimeters and 120. Yeah, we can have permissible joints according to that on the longitudinal way. So it depends on our bar diameter. So as we say before, because of that relation between force, stress transmitted to our concrete, if we have lower diameter bar thickness, we get to have, let's say, bigger distances for our expansion joints. So this is the design table you get to see when, as we increase the length of the balcony, so the lower should be the element or the steel element in accordance to that relation between force, stress, and transmission to the concrete. Okay, a little bit about our fire protection. Most of our products are rated to the RI 120 or 90, depending on the product, which is meant. This is the French nomenclature, but this is resistant, so it prevents. It need to withstand the mechanical capacity after the incident. It needs to be integrated, not allow the pass of gases or vapor. For example, in the core, you don't get to get this when the incident happened. And insulation, even in the event of a fire, it will remain the upper face, for example, within a temperature limit of 140. Sorry. So, okay, again, this is an example of a test we do in our lab. So this one is already open, but here was closed, and we have an isocore on both sides. And yeah, we put like an oven here inside. So we test this fire protection or fire resistance capacity. And you get to see it here. This is the end of the result. And well, you get to see that the balcony is still there. So it withstand even after the test, it's still on place. And yeah, the fire plate in the bottom is a little bit damaged, but not still there. And yeah, yes, that's pretty much it. We mentioned that before, or my colleague mentioned that, the approvals or certificates we have all around the world. In North America, I think for the Baltics, the most important will be the ATA. But yeah, we have approvals in all these other countries with all the regulations, also in China, Japan, Korea, and seismic places, as I mentioned before. Yeah, installation process, just a couple of words on that. This is how you install it. Yes, the principle is pretty simple. You just put it, once you have all your rebar on both sides, you can do it this way. Just wait until the end and just place it on place. It has here what it's called a tongue and groove, so you can put them together. This is what I wanted to point out here. You can install it even after you have all your reinforcement ready. So usually construction companies like that because they can put it at the last minute, you can say. This is another construction example, but this is on a construction site in Japan. You get to see it's pretty nice and clean. But they decide to install the isocorp actually before. This is where the balcony will be, so they install it before, and yeah, you can do that. Also like this in previous way. And a couple of words of the practical topic too. It's let's say you have 2 meters 70 centimeters balcony, so you will receive the pieces in length of 1 meter. This is the standard, but it's not a problem because you can cut it. You can have this cut even with a manual saw, and you can see, and the materials used for the isocorp makes possible to have a pretty nice cut, so it won't be a problem. Some of the installation process we've seen also some references before, but this is how it is in a precaster. You get to see it here. They're pouring the concrete for the balcony. Here is the element already placed, and this is how it's storage. You get to see all the balconies already here, and later they just grab it and put it in place and support it, and you can now pour the concrete to your slab, and you have the balcony all precast. As we saw before, also can be installing hollow core slabs. Within this other kind of isocorp, which is a steel-to-steel connection, but a little bit different, but the principle is the same. You have the isocorp attached to these steel plates, which is bolted to the hollow core slab. This is a possibility too if you don't have, let's say, uncovered ceilings here, and you can have the bolts passing. And it's not the only solution. Here we have also isocorp with the steel plates. Also it's bolt here. Just point out this thick steel plate. It's there, so it's inside. You get to see it. For example, it won't suffer for the thermal expansion or contraction because it's past our insulation, so it won't experience those movements as we mentioned before. For example, for our steel or elements in our thermal break system, which is exposed to the external conditions. Other thermal breaks. We have other kind of thermal breaks. I think my colleague also mentioned that, so just gonna do a quick recap. The concrete to concrete, concrete to steel, and steel to steel connection. Also this is usable for steel, concrete to wood connections if it's needed. And here's the one we saw at the beginning with the anchors. This is how it's used. Here is the way to apply it into a wall, or even if you have a step up or a step down, this is also useful because you cannot pass the rebar over there. So this is how it's installed, and at least you will need 175 millimeters, so you can have a solution in pretty much every situation. Also the picture for the parapets. We can have this solution, and the benefit is the same as balconies. We avoid this old-fashioned wrapping, you may say. So there's no need to waste all this material packing to having to pack the parapet actually, because we avoid all this insulation material, waterproofing, cladding system. Is way more convenient to do it like that. Also, we saw this one. Well, just to recap real quick. Of course, it's usually it's you cannot see it, right? You cannot see the isocorp, but this is just to show how it's placed on site. because it's always covered by the slabs or the element that it's connecting or the window frames. But yeah, this is how it's supposed to be placed. For example, this is a steel to concrete connection. And the other product also, the same. This for a balcony or for a space that wasn't there before, and you use it to create a new or to expand the area. And this way you get to seal the living unit with more money because of the balcony, of course. This is useful in that way. And yeah, the steel to steel connections. You get to see here the beams passing your facade. So this is where you place the product. And yeah, a couple of pictures of that. You get to see the models. For example, in this one, we have 4 models placed because of the size of the beam and the loads that we need to withstand. But yeah, you can have lighter connections, and depending on that is the amount of models we place over there. And yeah, to finish, some examples. We already saw some of those, but I want to point out this one. This is in Canada, the West Coast. It's a highly seismic area. So yeah, it needs to be considered because it's a pretty tall building, 52 floors, and you will have a seismic reaction in each floor getting higher and higher. And yeah, this is an example of how we use our isocorp, this type K in this product. And yeah, also in Canada, I like to show this one because you get to see here the perimeter of the balcony, that also it doesn't have to be online with my facade. And actually, if you remember, this is the project we saw for the design. Here is the column, and you get to see the balcony going inside the slab. And yeah, pretty much you see the situation on the corner is no problem. Other projects, for example, in hot environments, also it applies, right? It's not just for cold environments. This is in Texas, in the US, also a connection over there. And this other, which is a really iconic project, I think, this is a steel-to-steel connection. This Comandante Ferraz in Antarctica. This is a base from Brazil. And yeah, this is pretty interesting because they use here the isocorps behind this cladding. So yeah, here the energy is more expensive. Of course, bring everything to this place, and you will have big amount of condensations here if you don't treat this problem. So yeah, this is pretty cool project and pretty good way to use the thermal breaks. Steel to steel, also using in this attach this cladding in France. It's in the structure behind this part. Another example where we use it in hot or warm environments. It was used along this building here and the main tower. Different types of isocorp as the ones I showed them before. So yeah, in this case, to keep the warm or the high temperature outside. We saw this one here. It's of course we have a lot of projects in the Baltic states. Yeah, to point out here the thin balconies, as my colleague mentioned before. You get to see this is more aesthetic, not those big wrapping solutions you get to see, not so well looked for architectural purposes. Yeah, also the big cantilever project. And this is needs to be mentioned. This is a special isocorp. Yeah, we have our standard range of products, but we can do special solutions as this one because yeah, you just need to get in touch with us and we can work on a solution for that. It's even if the project is not well defined yet, the sooner the better to create this kind of special solutions. another project in Kaunas. We provide the concrete to steel connection here. So directly to the precaster. And they place them and attach them when they're making this beam. And they bring it to the construction site and just attach the balconies later. To finalize, some more examples that go on and on. Some interesting projects here in Korea too. A lot of projects that has been done, for example, with our tape K for concrete connection. And that's the end of the presentation. Thank you so much for your attention.